Well, hello, good people. Today we are talking about work, energy, and power. Now, this is the beginning of a new unit, and this is going to be a unit on work and energy and on momentum. We'll start our unit by talking about work and energy, and then we'll talk about different types of energy. We'll talk about conservation of energy, and then we'll end our unit by talking about momentum. Today we're going to start by talking about work, energy, and power. And to start, we have to talk about what work is. So we'll start with a quick definition for work. And I say that work, oh no, that was a bad letter K. Work is transferred energy. Work is transferred energy. It's energy that is transferred, and if you do work, then what you're doing is you're transferring energy. That's what work means. Now, in order to understand work, you would say, then we must understand energy. Well, actually, energy is defined as the ability to do work. Okay. Now, if you're looking at these two definitions, you might say these two definitions, if I were to give them a shape, I would call them a bit circular. Because if work is transferred energy, and energy is the ability to do work, then energy just means that if you have energy, you have the ability to transfer it. And that is totally and completely true. That is what energy is. It's if you have it, then you have the ability to transfer it. That's what energy is. And so we don't actually have a great definition in physics for energy, which is weird because we say that physics is the study of matter and energy, and yet we don't have a great definition for energy. The best way to understand energy is through examples of different types of energy, so we actually won't really be diving down deep into the definition of energy today. We'll come back to that when we come to more different examples of energy, but for today, all that you need to know is that work is transferred energy, energy is the ability to do work, so energy is what you have if you could transfer it. And energy, you can think of it today as pretty much like what you think of when you normally think of energy. So if you see a kindergartner running around a playground and you say, wow, that kindergartner has a lot of energy, yep, you're absolutely right. If you see a big explosion versus a little tiny candle and I asked you which one has more energy, you would probably say the explosion, and you would be totally right. If I asked you, hey, that's a very nice drink that you brought to class today, but you're going to need to dump it out because it's an energy drink and I only allow water. And you say, oh, but Miss Wilson, this drink gives me so much more energy. Then you're thinking in the right terms. A lot of what you've looked at before in previous classes has been chemical energy, so energy stored in chemical bonds. Today, what we'll be looking at is a little bit different. We'll be looking at the energy that something has because it's going fast, or the energy that something has because of where it is located in space. So that'll be the main types of energy that we look at in this class. But for today, you can, whatever working definition you have for energy in your head about what it is based on examples that you know from real life, that is going to work great for today. What you need to know is that work is transferred energy. It's moving energy from one place to another place. Now, in order to transfer energy to something, you have to apply a force for a distance. You have to apply a force for some amount of distance. Wait, I need something to use. Okay. Wow, this is so fun. Okay. Here I have a little cactus. This cactus's name is Connor. Connor came with the name Connor. I didn't name Connor. Connor, literally, like on Connor's little name tag here, it says, wait, I can make this big for you. 1 second so that you can really see. Okay. Here on Connor's name tag, it says Connor. That's how you know that Connor's name is Connor. Here's Connor. Oh, Connor waved hello. Wow, that's so cute. And here is my bear, which we shall call Bear. Now, if Bear and Connor are both sitting on the table, then you could probably imagine that Bear and Connor sitting on the table would probably have pretty similar amounts of energy. Probably not a lot. But if Connor said, I'm ready for takeoff, and I said, what do you mean, Connor? And he said, launch me across the room. I'd say, okay, Connor. And I'd grab Connor the cactus, and I'd take Connor, and I would throw Connor across the room. Hey, here's a quick question, just based on your instincts about energy. Who would have more energy? Bear sitting on the table or Connor flying across the room? You say, probably Connor flying across the room. Why? Because Connor's moving and Bear is not moving and Bear is still and Connor's going. And so you would say Connor probably has more energy. Well, in order to give Connor that energy so that Connor has more energy than Bear, in order to take Connor from a state of low energy, like if Connor's just sitting on a table, to a state of high energy, like flying across the room, someone has to come along and apply a force for a certain distance. We call that a throw. And so, here's what we would say is that anytime you want to transfer energy to an object, you have to apply a force for a certain amount of distance. That's the only way that energy is going to be added to something or taken away from something. It's not enough for an object to just have a distance, and it's not enough for an object to just have a force. Suppose that Connor was, Okay. Suppose that Connor was flying across the room at a nice constant velocity. If Connor's flying across the room at a nice constant velocity, well then he is experiencing a distance. He is going a distance, but if he's at a constant velocity, there's no net force. So even though Connor has energy, if he's going a certain distance, but there's no force, then there is no transfer of energy. In other words, if Connor is moving across the room at a nice constant velocity, energy is not being added to Connor, and energy is not being taken away from Connor. And so the total energy of Connor stays the same. No energy is transferred, and so no work is done. So you can't just have an object that's going for a certain distance. It has to be experiencing a force for that distance in order to add energy to that object or to transfer energy to that object. So in order for energy to be transferred, you can't just go a distance. You have to experience a force for that distance. Otherwise, you're not changing your energy at all. The other thing that's true is that you can't just experience a force. If I took Connor like this and I held Connor above my head like so, for a long time, Connor would experience a force because there's a force of my hand on Connor that is overcoming the force of gravity right now. So Connor would be experiencing a force. But Connor is not experiencing a displacement. If Connor is just sitting here above my head, is Connor's energy changing? No! Connor's energy is staying the same. Is my arm getting tired? Yes, because my arm is applying a force. But my arm is not applying a force over a distance. So I'm not changing Connor's energy. I am not changing Connor's energy. Connor's energy is the same. So there is no transfer of energy, which means that there is no work being done. So in order for work to be done, you need both a force and a displacement. Both of those are essential ingredients. That leads us to an equation for work that looks like this. Let's change our colors because we're crazy. Our equation for work looks like this. We say that work, in order for work to be work requires a force and a displacement. If you had to use one letter to represent work, then of course you would use the capital letter W. Notice that work in physics has nothing to do with what you understand work to mean in real life. In real life, you would talk about doing your homework. You would talk about how it was a lot of work to do all of your math problems. You would talk about how when you grow up and you get a job, you want to go to work every day. But work in physics is transferred energy. It has nothing to do with going to work. It has nothing to do with effort. When I hold Connor up above my head, that takes effort. That takes effort, but it isn't necessarily work. So you cannot think of work as having anything to do with work in real life because they're just totally and completely separate ideas. Work in physics is a force times a displacement. Now, let's talk a little bit about units here. The units of force, are newtons. The units of displacement, are meters. So that leaves us with the units of work being Newton meters. But all the good physicists of the world got very, very tired of saying Newton meters, Newton meters, Newton meters, Newton meters, Newton meters all the time. So they said we need something new. Some new units that are nice and sparkly. And so they said, let us call them joules. The sparkliest units in all the land. Except they couldn't have them like too similar to the jewels that you find in a jewelry box. And so to keep it nice and scientific looking and less sparkly, then they called it joules, but they spelled it this way. So work is equal to force times displacement, and work has units of joules. It is transferred energy. That's what work is. It's how much energy you transfer to an object. Now, before we continue on, there is one important part of this equation here that is missing, and that is that this force needs a special little subscript here. This subscript means parallel. It's two lines next to each other. And what it means is it means that the force, we don't care about all of the force. We just care about the part of the force that is parallel to the displacement. Let's take a look at an example here and you'll see what I mean. Actually, let's do this guy here. Okay. Here is a box. And this box is sitting on a nice, this box is sitting on a nice frictional floor here. You've seen this kind of thing before. And let's suppose that this force, or this box, is experiencing some forces. We would say, of course, that gravity is pulling down on this box. Let's say that there is some applied force at an angle. You say classic trope. I've seen it before, Miss Wilson. There's our applied force at an angle. And then let's do, actually, I'm going to draw that dotted line with something less extreme than this marker, because the marker is big. Did you guys notice I'm using the pen today? That's kind of a big deal. I never use the pen. But maybe it's a new era. Maybe it's pen era now. Okay, let's see. Here we go. There's the bell. Here's our angle theta. Okay, and then we of course do have a normal force, which is less than my weight here. So actually I'll leave it. You guys get the idea. I'll call that Fn, and then suppose that I have a frictional force that is slowing this guy down a little bit. We'll call it Fk, and you say all of this is just such old news to me, Miss Wilson. Why is this just old stuff? Can you please get me something new? Okay, I'm getting there. We're going to get there. Here's my question. First, is Fa doing work on this box right now? Is it transferring energy to the box? You would say yes, because before that box would just be sitting there motionless, which is kind of a low energy sort of situation. But if you have that applied force, it's adding energy into the box, making it go faster and faster and faster, making it a more and more and more energetic situation. So yes, Fa is doing work on the box. But not all of Fa is doing work on the box. Take a look. You know that we can break up Fa into its component parts. I don't like that arrow. You know that we can break up Fa into its component parts. I still don't like that arrow either. Sorry, let me try again. You know that we can break Fa. Why can I not draw an arrow that I like? I just want it to end there. Okay. You know that we can break Fa into its component parts. Here we have Fax, which is the x component of Fa. And here we have Fay, which is the y component of Fa. Which of the two, good people, is actually adding energy into the box? Is it Fax or Fay? Well, you say Fax, Miss Wilson, because that's the one that's actually making it go fast across the table. That's the one that's actually speeding it up. Is Fay actually doing any work at all? No, it's not changing its energy here at all. It's not making it more energetic. It's not making it less energetic. So Fax is the only force here that is actually doing work. This is why we say that F has to be parallel, or we need the part of F that is parallel to the displacement. If the displacement is this way, like if the box goes this far under the influence of Fa, if this is our displacement here, then the part of Fa that is parallel with the displacement is Fax. So this is crucial here because we would say you have to be in line with the displacement in order to actually be transferring energy. If you're not in line with the displacement, if you're not parallel to the displacement like FAY, then you're not actually doing any work. So in this case, FAX is doing work. FAY, not doing work. FN is also not doing work. And FG is also not doing work. FK actually is doing work, and we'll talk about that more momentarily. Okay. The next thing that I want you to notice here about work is that in this equation, force has a vector and displacement has a vector, and that is totally and absolutely correct. They both should, because don't we need them to have direction because we need their directions to be lined up with each other. But what you'll notice is that work here does not have a vector. And that's because work is transferred energy. It's how much energy gets transferred to an object. And energy does not have a direction. Energy does not have a direction, and you know this to be true based on your life experiences. Because how crazy would it be if you said, yes, that kindergartner running around the playground looks like they have a lot of energy to the north. You would never say that because that would be crazy. Or if I looked in your energy drink and I said, wow, nice energy drink, I feel like that will give you a lot of energy to the right. You would say that is a crazy way of talking. We never talk that way. That's because energy does not have a direction. So work does not have a direction, force does have a direction, and displacement does have a direction. However, even though work does not have a direction, work does have signs. So work can be positive or work can be negative. If work is positive, that means something, and if work is negative, that means something. What it does not mean is direction. It does not mean that the work is going in the positive direction or that work is going in the negative direction, because energy doesn't go in any direction. But what it does mean is if you have positive work, that means that energy is added to the object. And if you have negative work, that means energy is taken from. Oh, yeah, let's scooch that down. So sorry. Okay. Is taken from the object. Let's take a look back here at our box again. FAX, we would say, is doing positive work because FAX is adding energy to the box. The box has more energy because FAX is adding energy into it. It's going faster and faster and faster across the table because of FAX. So FAX is adding energy to the object. FK is taking energy away from the object. Notice that FAX is making this box speed up and speed up and speed up and speed up so that it's getting faster and faster and faster. But FK is slowing down the box. So FA puts energy into the box and friction takes that energy right back out again. So that if there was no friction, that box would be flying across the room getting faster and faster and faster and faster. But because there is friction, that friction is stealing some of the energy away and slowing it down. By the way, where does that energy go? The stuff that friction steals? It becomes heat. So you put in energy when you pull on FA, but then friction steals some of that energy away and turns it into heat so that it doesn't go quite as fast as it would if FK wasn't there. Here's something else that you'll notice, is that FAX is in the same direction as the displacement, but FK is in the opposite direction as the displacement. This is always true, that work is positive if the force that is doing the work and the displacement of the object experiencing the work are in the same direction. But work is negative if the force that's doing the work and the displacement of the object are in opposite directions. Okay, let's do a little example. Okay, suppose that I had Connor here. Suppose that Connor started down here, below where you can see him. And suppose that I slowly and gradually lift Connor up onto the screen like this. If I lift Connor up at a constant velocity, first, do you agree? If I'm lifting Connor at a constant velocity, then Connor's weight, gravity, is pulling Connor down, but the force of my hand is pushing Connor up. Here's a question for you. As I lift Connor up at a constant velocity, first, is gravity doing work? Second, am I doing work? Third, if gravity's doing work, is it positive work or negative work? And fourth, if I'm doing work, is that positive work or negative work? Go ahead and check that, think about that in your brain for a quick second, pause the video, make some notes to yourself. And now I'm gonna, oh gosh, wow, I am so glad we found no viruses. That is awesome. Okay, let's go ahead and talk about it. If I am lifting Connor up, my force is up and Connor's displacement is up. So I am transferring energy to Connor. I am doing positive work because my force is up and Connor is going up. Meanwhile, gravity is pulling down on Connor and Connor's displacement is up. So the direction of the force and the direction of the displacement are in opposite directions, which means gravity is doing work because there's a force that's applied over displacement. So gravity is doing work, but it's doing negative work. It's taking energy out of the system. Here's how I want you to think about it. Suppose that gravity was not here and it was just me and Connor, and I throw Connor up like this. If I throw Connor up like this, then won't Connor start accelerating until Connor would go up and then fly through the ceiling and then end up in the classroom above us? Isn't that true? But because there's gravity, even though I try to put energy in to speed Connor up, gravity takes that energy right back out again and takes that energy out to slow Connor down. So Connor is moving at a constant velocity because I put energy in, gravity takes it out, and so Connor goes on up. That is what we mean by the signs on our work. Try another one. Suppose that now that Connor is up here, suppose that I slowly lower Connor down like this. Is probably better to think about it like this. Wait. Okay. Suppose that I slowly lower Connor down like this. If I lower Connor down, am I doing positive work or negative work? And is gravity doing positive work or negative work? Okay, here's what you would say. You would say gravity is going down and Connor is going down. So gravity is doing positive work on Connor as he goes down. But check out what I'm doing. This is a little bit confusing for students, but let's sit here for a second. Do you see that right now the force of my hand is actually up on Connor? Do you see that? Connor is going down, but my force is up because I'm slowing Connor down. What it would look like if my force was down is if I got my hand on the other side of Connor and I pushed Connor down as Connor fell. That would be my force going down. But my force is actually underneath Connor, and my force is pushing up as Connor goes down. So I am doing negative work. And imagine it this way. Gravity is trying to put energy into Connor, making Connor go faster and faster and faster down. But I, at the same time, am stealing energy out of Connor because I'm slowing Connor down so that he doesn't fall as fast under the influence of gravity. So I do negative work, I'm taking energy out. Gravity is doing positive work, it's putting energy in. And that is what we see in that scenario. Okay, let's go ahead and try a practice problem. I'm going to get a new tab pulled up here. One moment. Okay, students, we are here to take a look at page 162, number 3. Here's what it says. A shopper in a supermarket pushes a car with a force of 35 newtons directed at an angle of 25 degrees downward from the horizontal. Find the work done by the shopper on the cart as the shopper moves along a 50.0 meter length of aisle. Wow, 50 meters, that is a pretty long aisle. This shopper must definitely and most certainly be at Costco. Because where else do you have aisles that long? Okay, let's take a look. First, I'm going to start by drawing a diagram of the situation. When I draw a diagram of the situation, I'm going to draw a shopping cart. Now, you do not need to draw a shopping cart because you might say, Miss Wilson, I am artistically challenged and a shopping cart feels hard. If that feels hard for you, that's fine. Then you can just draw a box. But I am going to draw a shopping cart to exercise my artistic talents and to learn and grow. So there is my shopping cart that I have drawn. Now, let's show the force that's happening here. When you push a shopping cart, don't you push it at an angle down? You're not going to push a shopping cart straight horizontal. You don't say, yes, let me push my shopping cart now. That is not how you push a shopping cart. You do not lower yourself so that you are only applying a perfectly horizontal force. No, you apply a force that is lined up with your handle here. So you apply a force down at an angle like this. Like any free body diagram, we draw that force starting on the object and pointing away from the object like this. It says that this shopper in her supermarket pushes the cart with a force of 35 newtons directed at an angle of 25 degrees downwards. Okay, so here is our, here is, let's do this. Here's our angle, theta, which we'll label here. The problem tells us that theta is 35 degrees downwards. Oh, wow, gosh, that was embarrassing. Our textbook says that that angle is 25 degrees. And it says that the applied force is 35 newtons. So I'll write that here. My applied force is 35 newtons. Why can I not write 35? Allow me to try but once more. 35 newtons. Okay. Next, we are looking for the work done if the shopper moves along a 50.0 meter length of aisle. So delta x is equal to 50.0 meters. Here's what I'm thinking, and I'm going to draw this in my picture here. If this is my FA, I'm going to say that this way is going to be the direction of my displacement, and so I'm going to label that as being true. Then, here's what I'll say next. I'll start with an original equation. I say the total amount of work done is equal to my force, but not my whole force, just the part of the force that is parallel to the displacement that is taking place, and that will tell us how much energy is transferred to this cart. For the amount of energy transferred to the cart, I want FAX will be the part of the force that's parallel, and I multiply that by delta x. Now, before I do anything else here, in order to get rid of that parallel, I have to answer two questions. First, I want to make sure that the force that I'm using is just the part that's in line with x, which I did that because I said FAX, not FA. Then, I also need to decide, are these two going in the same direction or are they going in opposite directions? In other words, is this force transferring energy to the cart or taking that energy away from the cart? And looking at this picture, I would say, I do think that the force is going in the same direction as the displacement, so then I can leave this as positive here. Then, I write in for FAX the way that I find FAX. Looking at my diagram here, there's a component of this force here, FAX, that is in line with the displacement. Then there's another component here, which we shall call FAY, that is perpendicular to the displacement. Why did that not make a Y? Okay, so in order to find FAX, I check out my little diagram here, and I say which of my trig friends would I like to use. I say cosine looks like the one to get the job done, so I say FA times the cosine of theta. If you need to work to find this off to the side, great, work to find it off to the side. Then I'm going to multiply that by my delta x. FA, in this case, is 35 newtons. I take the cosine of 25 degrees, and my displacement here is 50.0 meters. We take that, we plug it into our calculators, and we get 1.6 times 10 to the third joules. Now, wow, my numbers got crazy. That might seem like a very big number to you, but really, in terms of energy, that is not a very big number at all. A joule is not much at all. It's hardly any energy. So 1.6 times 10 to the third joules is totally reasonable. I don't need a sign here. I will just let the positive or the negative speak for itself because it's not a direction. And there's our practice problem. Now, before we go today, there is one more topic that we are going to talk about that we have not yet addressed, and that is the topic of power. So let us discuss power. Power is the rate at which energy is transferred, or the rate at which work is done. There is a difference, good people, between lifting Connor like this. Okay, between lifting Connor like this and lifting Connor like this. There's a difference between those two things. And the difference is the rate at which energy is transferred. In the second scenario, energy is transferred to Connor way faster than in the first scenario. The way that we describe this, the way that we talk about this in physics is with the concept of power. Power is the rate at which work is done. Well, you already know some things about rate. If you had to use one letter to represent power, we would use capital letter P, which is beautiful and glorious because that is what we use. Power, please use capital letter P, not lowercase letter p, or it's going to very quickly become confusing. So please use capital letter P for power. Power, since it's the rate at which work is done, is work divided by time, because that's what a rate is. It's a change in something over a change in time. In this case, it's work means change in energy. So it's a change in energy over a change in time. And there is your equation. Oh, I forgot to box the equation on the last page. Do box it and do put it in your bag of tricks because it is significant. I don't know if I boxed it or not, but I'm feeling like I definitely did not box it. Okay. Power is the rate at which work is done. Let's talk about your units here quick. The units of power. Well, the units of work are going to be joules. The units of time are going to be seconds. So the units of power is joules per second. But all the good physicists of the world got very tired of saying joules per second, 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 joules per second. So they said we need something new. We need something quick, something sharp. And they said, let us call it watts. And they said, yes, we shall represent it with the capital letter W. Is that confusing? Yes, because work is also capital letter W. So here's how you will know the difference. If you have a capital letter W in an equation, that means work. If you have a capital letter W after a number, that means it's units, and that means it's watts. Let's go ahead and try a quick practice problem with this one. We're going to take a look at page 181, number 3. Allow me to flip in my textbook, and you may do the same. Page 181. Nope, that's page 200. Wait, go back. 186. We're so very close. 184. 182. The suspense is building. 181. Hey, on 181, do you see that there are two boxes? There's a purple box and a blue box. When you do your homework, can you please do the questions in the purple box? Okay, here's what we have. A rain cloud contains 2.66 times 10 to the 7th kilograms of water vapor. How long would it take for a 2 kilowatt pump to raise the same amount of water to the cloud's altitude, which is 2.0 kilometers? Okay, so here's the situation. It's saying we've got a rain cloud that has some water in it. And the question is basically the way that the cloud forms is through evaporation. But if we had a pump and we tried to pump that water into the sky, how long would it take to pump all that water into the sky versus like what evaporation does? Okay. So here's where I start. I'm going to start with my knowns and unknowns. Here's what I know. The mass of the water that I'm going to try to pump into the sky to make a cloud is 2.66 times 10 to the 7th kilograms. Our pump that we are going to use to pump it into the sky is a 2.00 kilowatt pump. That means that this pump has a power rating, which means it can put out this amount of energy in a certain amount of time, or in 1 second, I suppose. It can put out 2.00 times 10 to the third watts. Notice it gave it to me in kilowatts. I did a quick unit conversion here to get it into watts, and that will serve me much better. The displacement of this guy, how high I'm lifting up the water, which I call it here a delta X. You could also call it a delta H if you wanted to, or a delta Y if you wanted to. You can use whatever symbol you really want to represent that change in height here. I'm going to pump this water from the ground up to where the cloud would live, which is, let's see, it says 2 kilometers in the air. I'm going to do another quick unit conversion. I'm going to change that 2 kilometers to 2 times 10 to the third meters. And I'm looking for how long it would take. That's a certain amount of time. Okay, I start with my original equation here. I say that power is equal to work divided by time. Great. Now here's the problem, is that I'm looking for a time. I have a power, but I was not given a work. Luckily, I can find work, because I know that work is the force that is parallel to the displacement times the displacement. Now, here's the next question. If I wanted to find this force, that's how much force it takes to lift the water, well, the amount of force that it would take to lift the water would be equal to the weight of the water. The amount of force it takes to lift something is just as much as it weighs. So if the water has a mass of 2.66 times 10 to the 7th kilograms, then I could find out how much it weighs. And if I know how much it weighs, I know how much force it takes to lift something. The amount of force it would take to lift this is going to be Fg, the weight of the water. You could also look at this in a free body diagram type way. Here I have water, Fg is pulling it down. If I want it to go up, the bare minimum amount of force that I have to put in is going to be my force applied. Do you see that my applied force is going to have to equal the weight in order to get this thing to go up? So, Fg times delta X divided by delta T. Then I have a formula for Fg, and that is, I know Fg is equal to mg. So that's going to be mg times delta X all over delta T. Now I can plug in numbers because I have m, I know g deep down inside my heart, I have a delta X and I have a delta, oh gosh, no, I can't even plug in numbers yet. What am I doing? I have to rearrange for delta T. Oh gosh, that was almost embarrassing. Okay, delta T is equal to mg delta X all over the power. And now I can plug in numbers. When I plug in numbers, I plug in 2.66 times 10 to the 7th kilograms times g, which is 9.81 meters per second squared, your favorite number in physics, times my delta X, which is 2.00 times 10 to the third meters, all divided by power, which is 2.00 times 10 to the third watts. Now I really am running out of space here, so you would do this in the not way that I'm doing it, but I'm going to write that that gives me that delta T is equal to, if you plug this into your calculators, that's 2.61 times 10 to the 8th seconds. My friends, 2.61 times 10 to the 8th seconds is an enormous number. That number, if you did a quick unit conversion, would come out to be 8.27 years. It would take us 8.27 years to make a cloud of this size with this kind of pump. Aren't we very thankful for evaporation? And that is all for today, folks. I hope you have a wonderful rest of your day. Today we talked about work and power. I hope you have some understanding of what work is. I hope you have some understanding of what power is. And that you understand really deep down the why behind this equation and our other equation is really what super matters today. I hope you have a wonderful rest of your day, and I will see you all next time. Bye, good people.